Let's look now at section 8.1 and let's talk about basic integration rules. In this section, we're going to be reviewing the integration techniques that you've already seen in Cal 1 and in this first half of Cal 2. This is to make sure that we have the basics down before we start into Chapter 8, which is more advanced integration techniques. So let's remind ourselves of what we know so far, because even though it is substantial, meaning we can do a decent amount with it, it's really only breaks down into a few basic categories. So first of all, we don't have a lot of basic integration formulas. In reality, we have three of them, which get abused along with the substitution technique. So here we say, okay, the power rule, the integral of x to the power of n. Well, you add 1 to the power, divide by that new power, and then add c, your constant of integration. There we go. That's essentially it. To integrate something which a variable to a power, you use this. Now, the exception to that is if that power is minus 1, in which case use the logarithm rule. X to the minus 1, or 1 over x, same thing. Here we write it as integral du over u, and that's equal to the natural log of the absolute value of u plus a constant of integration. This is the exception to the power rule. X to the minus 1, or in this case u to the minus 1, is not going to follow this technique, because if you had x to the minus 1 and followed this technique, negative 1 plus 1 is 0 over 0, which is kind of a problem. Huh? And then we have the linearity property, which we learned in Cal 1, which says if you take the integral of a sum or difference, you can separate that as the sum or difference of the integrals. You can separate the integral of the first part plus or minus the integral of the second part. And if your function that you're integrating happens to be multiplied by a constant, you can always factor that constant out. And same thing here, you can factor that constant out. And this is called the linearity property. You're allowed to factor out constants. Notice these are not variables, they're not functions of x, they're just regular constants, a and b. And here, these functions can be split up into several small integrals. And that is essentially it. These are the three basic integration forms that we've seen so far. And the only reason that they don't always look exactly like these three formulas is because we use substitutions a decent amount of times. We have the substitution technique says take part of your expression, take a function that's in the integrand, call it u. So then the new differential is going to be the derivative of that function times the differential of the original variable, or in other words, f prime of x dx. Now, we've seen a few other more advanced integrals, for example, the exponential, e to the x, and we've seen the inverse trig functions and the hyperbolic functions, but here that's not going to fall into the category of basic integrals. Basic integrals are the ones that we essentially see in Cal 1. Okay. Now, substitution is a great technique, and in fact, it's going to be the single most useful one. Throughout this course, and really any course that involves integration, or through any technique that involves integration, substitution will play at least some small role, if not sometimes the central role. However, in order to get the substitution to work out, sometimes you need to manipulate the integrand. You need to take the thing in here and play with it a bit, so you rewrite it in a form that's more manageable. To those ends, we have a few algebraic manipulations and a few trigonometric manipulations. The trigonometric manipulations are just the trig identities, the trig formulas, the ones that we learn in trigonometry. The double angle formulas, the half angle formulas, the power reduction formulas, sine of 2x, cosine of 2x, tangent of 2x, half angle formulas, sine of half x, cosine of half x, tangent of half x. Power reduction formulas, sine squared of x can be written as what? Cosine squared of x can be written as what? Well, it can be written as lots of things. Okay, how can they be written so that the power goes down? How can I write sine squared of x in expressions that don't have a square anymore? Things like that. The Pythagorean identities, sine squared of x plus cosine squared of x equals to 1. And there's a couple of others that are equivalent. And finally, alternate representations. You can always write any trig function in terms of any other trig function. Is tangent of x not useful in your integral? Okay, maybe think of it as sine of x over cosine of x. Is sine of x not useful in your integral? Okay, well then maybe think of it as the square root of 1 minus cosine squared of x. There's other ways of representing any trig function because all 6 of them are related to each other. All right? So here, this is really just, hey, do you remember your trigonometry? Not even the more obscure parts like the sum and difference formulas, the product of sum formulas. Those do show up from time to time, but they're a lot less likely to occur. These show up a lot more often for what we're going to be doing. So really the question is, hey, remember trigonometry? Yeah. Remember the chapter on identities? Yeah. Remember the first half? Yeah. Okay, you're good. That's all we need. Algebraic manipulations can be a bit more extensive, but again, we don't use all of them equally. There's a few that are used more often than others. So let's see here. What algebraic manipulations do we want to use? One is expanding by distribution. Basically, if you have x plus 1 to the third power, that might be difficult to work with, whereas x plus 1 times x plus 1 times x plus 1, that's equivalent. But now, if I multiply this out, x to the third plus 3x squared plus 3x plus 1, that might be a lot simpler to work with. So depending on your situation, you may want to keep it as an expression to a power, or you may actually wish to expand it by distributing, by multiplying it out. Thinking back to algebra, distribution is the proper term for multiplying polynomial expressions. Okay. The second one is somewhat trivial. There's not a lot of effort that goes into doing it, but it just pays to remind you that it is something you can do. If ever you have an expression that has several terms in a numerator of a rational expression, for example, we have x plus 5 over x squared minus 1. That in and of itself might be meaningful. That might be something we want to use. However, it might also be simpler if we separate it. We can say x over x squared minus 1 plus 5 over x squared minus 1 and separate it into two separate expressions. That's not anything difficult. Obviously, all we did was you say, okay, make that one first and then separately that one second. And that's all really it'll ever be. All right? This isn't a difficult algebraic thing to do. It's just a good idea to remember that you can do it. You can separate things out. And the reason we want to be able to separate things out is, again, because of the linearity property. If things are separate, we can separate them into different integrals. And each of those integrals might be easier to work with than the original. Okay. Completing the square is useful, especially when we're going to be looking at trigonometric expressions. And as we already saw in chapter 5, looking at the inverse trig integrals. Completing the square, where you take something that looks like x squared plus 2x plus 3, and you rewrite it as the sum or difference of squares. Namely, for this problem, you would have x plus 1 squared plus 2. Right? These are equivalent. If you multiply this out and add 2, it'll give you that. But as the sum or difference of squares, you may be able to do things with this one that you couldn't with this one. It's kind of going in the opposite direction of expanding. Sometimes you want a polynomial. So you take something that's written as a power and expand it. Other times you don't want a polynomial. So you take your polynomial and you condense it down into some other form. Okay? Adding and subtracting terms, then simplifying. This is one of my personal favorites because it looks fancy. It looks like something that could take a lot of effort away from you. It could save you a lot of effort, but it's very straightforward to do once you get the hang of it. So, for example, let's say you had an expression that looked like, let's go with this, x squared over x squared plus 1. Okay, well, that's an improper expression, right? Your numerator's power should be smaller than that of your denominator. If the power of the numerator is greater than or equal to, the first thing you want to do is divide. Now, of course, one thing you could do is divide. You could use long division, or if the numerator is linear, you could write using synthetic division. But either way, long division or synthetic division will take a few minutes, right? Especially long division. This is always one of my favorite techniques because, again, it's useful in so many different categories. It's useful in not just integration and differentiation, but really anywhere that you're doing algebra or arithmetic. You say, okay, I want to divide this. You know, if that just had an extra +1 there, that'd be great because everything would just cancel out and I would get 1. Okay, so go ahead and add 1. But now you say, well, you can't do that. That's different. That's a different problem than what you started with. Okay, so then go ahead and subtract 1. Well, yeah, but then nothing really happened. +1 minus 1, those just cancel out. That gives me 0, and I'm back where I started. Okay, so don't let them cancel out. Take this and split it like we have up here. You can write this as x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. And now that's 1 minus that. So 1 minus 1 over x squared plus 1. And there we go, dividing without any of the extra mess. This technique comes in handy for dividing, sure, but it'll also come in handy in completing the square. If you have a hard time going from here to here, you might say, oh, well, look, x squared plus 2x plus 1. If this was x squared plus 2x plus 1 instead of 3, then things would be easy. I know how to factor x squared plus 2x plus 1 as a perfect square. Okay, well then go ahead and do that. Go ahead and write that as plus 1. Okay, there we go. Yeah, but now that's a different problem. Okay, so say minus 1. Oh, okay, well now if I group these together, that factors as x plus 1 squared. And then put these together, 3 minus 1 is 2. And there we go. So a lot of the algebraic techniques that you learn, essentially the long way, long division and completing the square and things like that, you can make them slightly faster by using this technique of adding and subtracting terms and then simplifying. Be very mindful of this technique. It is something that's very useful and very nice to use, but you got to make sure that you're doing it correctly. If you know the technique the long way, you may wish to compare the results the first few times you do that, because as you get used to it, it's very easy to abuse this and use it at a time when it should not be used. Right? So just be mindful of that. This is a very useful, very powerful, and actually very simple technique, but make sure you're using it properly. One way to do that is just subtract these and it should give you back what you started. Same thing here. If you multiply this out, it should give you back where you started. Eventually you get used to it to the point where you don't have to double check yourself, but the first few times that you do it, you might want to give that a check. All right. So these algebraic manipulations. Oh, and I guess I should just say factor. That's the last one. Don't forget you can factor stuff, and well, just factor. Right? That's something you've been doing at pretty much every class since pre-algebra, right? So just factor. So these algebraic manipulations, combined with these trigonometric manipulations, can change just a few basic integrals into hundreds of different problems. And going the other way around, you can take hundreds of different problems and using just a few algebraic and trigonometric manipulations, use a few basic integrals to solve, right, or to integrate. So let's go ahead and take a look at some examples of using some basic integration techniques along with some of these manipulations to integrate. If you note that a lot of these problems are familiar, if you say, well, wait a minute, I already knew how to do that. Well, good. That's what this section's about. It's a review of what you've seen in Cal 1 and maybe a little bit of what we've seen in the first part of Cal 2. If this entire section is very, very boring to you and you say, yeah, I already knew all that, perfect. You're in a very good position to move forward. If not, if some of these techniques are new to you and you think, I never learned that or I never saw that, you might want to double back and look at this section again and pay extra attention to the assignments in this section, the videos in this section, or any other material in this section because it's necessary to move forward through Chapter 8 and beyond that. So let's take a look at some examples. So we'll start off nicely, something without a lot of effort. Let's integrate x plus 2 over x plus 1. Okay, well, this looks a lot like this. I have a power in the numerator that is equal to or greater than the power in the denominator. So before anything else happens, I should probably divide that out. Now, of course, I could use long division or even synthetic division, but personally, I like this. I'm going to say, well, look, if this was just x plus 1, things would be great, because then I could just have x plus 1 over x plus 1, and I'm done. Okay, so let me add a 1 there. That way it's x plus 1. Well, yeah, but you can't just add 1. It changes the problem. Okay, so subtract 1 to balance things out. So here I can rewrite this as the integral of x plus 1 plus 2 minus 1 is 1 over x plus 1. Like that. But of course, now I can split this. I can say, okay, that's the integral of x plus 1 over x plus 1 plus 1 over x plus 1 dx. And now that simplifies to give me the integral of 1 plus 1 over x plus 1 dx. And now once it's split this way, I can go ahead and use linearity to separate that. That's the integral of 1 dx plus the integral of 1 over x plus 1 dx. But now those are just two basic integrals. I can use the power rule on this one. The integral of x to the n is add 1 to the power divided by the new power. Here, this is like saying 1x to the 0. So I can add 1 to the power divided by the new power, and I get 1x to the 1 over 1. Or in other words, I just get x. Plus, here, if I integrate 1 over x plus 1, that's this right here. Hey, look, x plus 1, I can call that u. In fact, let me write that down. X plus 1, let me call that u. Okay, well then du is going to be the derivative of this, which is just 1, times the differential of the original variable, the differential with respect to x. So you can think of this as 1 over u times 1 du, or more simply du over u. Yeah, that's exactly what this basic integration rule tells me. Integral of du over u is the natural log of the absolute value of u. So this becomes the natural log of the absolute value of u, but since u is x plus 1, we'll just pop in x plus 1. And then don't forget, an integral is not a unique result. The antiderivative of x plus 2 over x plus 1 could be x plus natural log of x plus 1, or it could be x plus natural log of absolute value of x plus 1 plus 1, or x plus natural log of absolute value of x plus 1 plus 2, or plus 3, or plus 4, or any constant. So here, instead of spending the time writing out all of those different results, we say, well, they're all the same except for that constant, so we put in our constant of integration. Note that without that expression, you are missing all but one answer. Here, the integral is a family of functions. Here, there's an infinite number of functions. This plus 1, this plus 2, this plus 3, this plus 4, plus 5, plus 6. There's an infinite number of results here. Without that, there's only one result. So keep that in mind. Without this, you're missing most of your answer. So that is our result. Let's see another example. Let's consider the integral of the sine of 2x dx. This one, there's a couple ways you can actually go about it. With an integral that involves an algebraic manipulation, you might have one way to do it. You might have two ways to do it. In some cases you have a lot, but usually you just have one, maybe two. Trigonometry, because of the flexibility of trigonometry, because of the number of different ways you can rewrite trigonometric expressions, oftentimes you'll have several ways of doing even basic problems. All right. So here, I'm going to show you two different ways to do this one because they both highlight two different techniques. So I'll just do this two separate ways. The first one, I'm going to use just regular substitution. note that I have sine of 2x dx. Well, I know the integral of sine of x dx. That's just negative cosine of x dx. Well, yeah, but I don't just have x. I have 2x. Okay, well, take this thing and use it as a substitution. After all, that's when you use substitution. When you have something that looks almost exactly like what you know how to do, except for this one part. Okay, so take this one part and call it something simpler. I'm going to take u and call it 2x. So du is going to be the derivative of this, which is just 2, times the differential of x, so 2 dx. Well, right here, I have just dx, not 2 dx. Okay, so divide both sides by 2. This will give me 1/2 du equals dx, just like that. So now, this is going to equal to, and I'm going to have the sine of u. In fact, let me use that red marker, or that red pen here. That's going to be the sine of u, and then your dx is 1/2 du. So that's sine of u 1/2 du. Now again, because of linearity, if I have a constant multiple, I'm allowed to just factor that out. So I can write this as 1/2 the integral of the sine of u du, which of course I know how to integrate as 1/2 times the negative cosine of u plus a constant of integration. That negative can just factor out. So we can write this as negative 1/2 cosine of u plus c. But of course, u is a stand-in for 2x, so we can always write that this way. We can write this as negative 1/2 times the cosine of 2x, just substituting u for 2x again, plus my constant of integration. And that's my result. Now let's take a look at another technique that's going to do the exact same problem, and it's going to look rather different, and that's okay, because as we've seen since trigonometry and through pre-Cal and even a bit in Cal 1, trig functions are a little unwieldy. They can take many different forms. So here we're going to write the same integral of the sine of 2x dx, but now instead of using a substitution on this, what I'm going to do is I'm going to say, well, sine of 2x, forget calculus. Since trigonometry, I've known that I can rewrite this using the double angle formula. So this can be written as the integral of, instead of sine of 2x, I can write that as 2 sine of x cosine of x dx. Now, of course, 2 is a constant, which, using linearity, I can factor out. So it's going to be 2 times the integral of sine of x cosine of x dx. I wish I could separate these, but I can't because linearity only allows me to factor out constant multiples. These are not constants, so I can't factorize them out. And linearity allows me to separate sums and differences. That's not a plus or a minus, that's a product. So unfortunately, I cannot split those. But what I can do is notice that the derivative of the sine of x is the cosine of x. So I can use a substitution now. If u is equal to the sine of x, then du is cosine of x times the differential dx, which is exactly what this is. So I can write this as 2 times the integral. Sine of x is just u. Cosine of x dx, that's just du. Just like that. And so now, the integral of this just uses the power rule. Okay? So here I can write this as equals to 2 times u to the 1, not u to the 1/2, u to the 2 over 2 plus a constant of integration. Just using the power rule, that's u to the first, add 1 to the power, divide by the new power. Note, of course, that these two divide away, And so we're just left with u squared plus a constant of integration. But of course, u is a stand-in for the sine of x. So let's pop that back in. So here this suggests that our result is going to be sine squared of x plus a constant of integration. Note how different these look. That's a power of the sine of x, and this is a multiple of the cosine of 2x plus constants. That is not a mistake. Both of these are correct, and using trigonometric identities, you could confirm that this is equal to that, or vice versa. You can confirm that this is equal to that. Which one is correct, though? Which one is the better answer, the simplified one? They're both fine. There is no reason why this one is better than that one or vice versa. So whenever you're dealing with integrations, especially with trigonometric functions, although sometimes with even algebraic expressions, you'll note that you'll have several different ways to get to an answer, several different techniques, which there's no reason why one has to be favored over the other. So find a way that works, and that's sufficient. That does mean that throughout this chapter, it's going to be slightly frustrating when you do your assignments. You will, out of the textbook, you'll have a problem, you'll do the problem, and you'll get an answer. And then you'll go to your answer guide in the back of the book where they give you the answers, and they'll write this one. And you'll sit there going, what did I do wrong? And, well, maybe you did do something wrong. Maybe you made a mistake and your answer is incorrect. Or maybe there's no mistake and they just chose a different way to do it. So keep that in mind. Throughout this chapter especially, it'll happen a little in other sections as well, in other chapters. But throughout chapter 8 especially, you'll note that the answer guides are, I wouldn't say useless, but a lot less useful than usual, because they may have chosen one technique, whereas you chose another, and the answers will look somewhat different, in some cases radically different, and both are correct. So just be mindful of that. Just because your answer looks different doesn't mean it's wrong necessarily. So let's have you try one. Let's have you integrate, let's go with this one. 1 over x natural log of x dx. So give this a try. This uses nothing more than basic integration techniques. There is going to be a substitution involved, so go ahead and give this a try. Pause the video and give yourself as much time as you need. And once you have a result, go ahead and unpause and we'll go through it together. All right, so let's take a look here. There isn't much you can simplify, right? There's not much here at all. So a substitution. Well, let's see. We could take x and call it u. Yeah, but that doesn't do anything. That just makes it 1 over u natural log of u du. Taking just the variable and calling it u is never the right way to do it, because all you're doing is changing one letter for another and nothing else. You gain nothing else. So what we want to do is we want to pick something a little bit bigger. We might choose x natural log of x, or we might just choose natural log of x. The correct choice is going to be whatever you choose needs to have its derivative within the problem. So here, if I choose x natural log of x, what's the derivative of x natural log of x? Well, using the product rule, the derivative of the first part times the second plus the derivative of the second part times the first. So that'll be natural log of x plus 1, which I don't have here. I don't have a natural log of x plus 1 or anything like that. So that means that this entire denominator is not a good choice for u because its derivative is not in the problem. So x is too small, x natural log of x is too big, so natural log of x seems like a good choice. Sort of by process of eliminations. That's too small. That's too small. The whole thing is too big, so maybe just this part. All right, so let's give that a try. If u is equal to the natural log of x, then du is going to be the derivative of the natural log of x, which we know is 1 over x dx, which is exactly this right here. So here we can write that as the integral. that 1 over x dx, that's just du, over the natural log of x, that's your u. So that's du over u. But that is one of our basic integration formulas. If you have the integral of du over u, that's the natural log of the absolute value of u. So this equals to natural log of the absolute value of u plus c. But of course, u is a stand-in for the natural log of x. So here we get an interesting looking result. We're going to have the composition of the natural log with itself. We're going to have the natural log of the absolute value of the natural log. Plus a constant of integration. Okay. Just like that. All right, let's try another one. Go ahead and find the integral of 4x squared over 25 plus 4x squared. Go ahead and pause the video and give this one a try. You may find more than one way to do it. So see what is the way you can come up with. And once you have a result, go ahead and unpause the video and we'll go through it together. All right, so let's take a look here. Okay, if that just had an extra plus 25 right there, this would be the easiest problem in the world. That would just reduce down to the integral of 1. Okay, so let's go ahead and do that. Let's go ahead and add 25 right here. But now, I subtract 25 right here to balance things out. Okay, so now this is going to become the integral of 25 plus 4x squared over 25 plus 4x squared minus 25 over 25 plus 4x squared dx. These two come together, and I can split this one aside. The reason I keep these together is because now this is just the number 1. So this will give me the integral of 1 minus 25 over 25 plus 4x squared dx. Using linearity, I can now separate these. I can write this as the integral of 1 dx minus the integral of 25 over 25 plus 4x squared dx. And here that 25 in the numerator, since it's a constant, I'm going to factor that out. Just like that. You might ask, why don't I factor out any of these constants? It's because you need something that's a constant that's common to every expression here. The whole thing here is being multiplied by 25 when we say 25 over this. Here only this term is being multiplied by 4. Right? And here this isn't the product at all. It's being added. Okay. So when you do this, pull out the 25, you're actually factoring. And just like with factoring in algebra, it has to be a common factor, common to the entire expression. Okay, so now this first part is nice. It's the most basic integral that we ever learned. The integral of a constant with respect to x is that constant times x. Or in other words, you just get x. Minus 25 times. Okay, now this one you'll recognize from chapter 5. 1 over the sum of 2 squares. So here, I'm going to write this as the integral. So I'm going to take this part right here. And I'm going to write this as the integral of 1 over, now this is the square of 5, plus this is the square of 2, and this is the square of x. So together, it's the square of 2x. So the integral of dx over constant squared plus variable squared. That's an arctangent. All right, recall that the arctangent looks like this. If you take dx over a, oh, I guess I should say that's, let me write this way. So that's going to be du over a squared minus u squared. That's going to equal to 1 over a times the arctangent of u over a plus your constant. Du over a squared, oh, there should be a plus u squared is equal to 1 over a arctangent of u over a plus c. And that's what we have here. Well, almost. After all, here, if I'm calling that u, that numerator is supposed to be du. Oh, well then du is 2 dx, not just dx. So I need an extra 2 here. Okay, well let's pull the same trick that we have up here. If you need some constant, you can always put it in and immediately take it back out. Once again, in order for this to fit this pattern, it's very close. That's constant squared plus variable squared, but then the numerator needs to be the derivative of this variable times dx. Well, we already have the dx, but the derivative of this variable is just 2. Okay, so I'm missing a 2 there. So up here, I needed to add a 25, so then I immediately subtracted a 25. Or here I don't need to add 2, I need to multiply by 2. Okay, so let me immediately divide by 2. These 2 would cancel out if I let them, but if I don't let them cancel out, this comes together to give me exactly this. So I can write this as x minus, here that's a constant, let me just factor that out, 25 over 2. I could factor out that 2, but I don't want to. I want to leave that in there so that it looks exactly like this. This is the integral of 2 dx over 5 squared plus 2x, quantity squared. And now that's exactly this form. That's du over a squared plus u squared. And so that's going to give us x minus 25 over 2 times. I'm going to have 1 over a, which in this case is 1 over 5, times the arctangent of u over a, which for us is going to be the arctangent of 2x over 5, all right, u over a, plus our constant of integration. Here, this reduces down a bit. 5 goes into 25 5 times. And anyone who's tempted to divide this 5 by this 5, you really need to go back and review how the trigonometric functions work. They're not linear operations, so you can't do that. Same thing with these 2's. The argument inside of a nonlinear function, you can't just cancel out with the numbers out here. So every semester I'll have one or two people who try to do that. Don't do that. So here this will give me x minus, that's 5 over 2, times the arctangent of 2x over 5 plus some constant of integration, which makes us happy. All right, as our last problem, go ahead and try. The integral of e to the x over e to the 2x plus 2e to the x plus 1 dx. Okay. Note e to the x appears several times, in this case e to the 2x. A substitution right off the bat, right at the very first step, that might be a good idea. So go ahead and give this a try. Go ahead and pause the video, give yourself the time that you need, and once you're done, go ahead and unpause and we'll do it together. All right, so let's take a look. Obviously, e to the x appears everywhere, so that might be a good choice for our substitution. Now, we'll see in later sections that the obvious choice for substitution isn't always the correct one. But, I mean, if it's obvious, we may as well give it a try, yeah? E to the x appears over and over again. And whatever appears over and over again is usually, not always, going to be a good idea for our substitution. Okay, so u equals e to the x, and so du is equal to the derivative of e to the x, which you'll recall from Cal 1 is exactly itself. E to the x is the one function that has the distinction of being its own derivative, times the differential of x. Okay, well, there it is. Look, e to the x dx. E to the x dx. That whole numerator is your du. All right, so let's go ahead and do that. that's going to be the integral of this whole thing. That's your du. All right. Notice that if u is equal to e to the x, that means that u squared equals e to the x quantity squared, which is the same thing as saying e to the 2x. So here, that e to the 2x is u squared plus 2 times u plus 1. All right, so that looks a little simpler. No more exponentials, and we have polynomial expressions left. Oh, that's already been absorbed. That and that together are du, so I don't need another dx here. Okay, so now, if this was polynomial, things would be great. You say, well, that is polynomial. Yeah, but it's in the denominator, so this is a rational expression. As a whole, this is a rational expression. Okay, well, I recall from chapter 5 that whenever I have a quadratic polynomial in my denominator, I might want to complete the square, and maybe this turns out to be an arc function, arctangent or something. But I look at this and I realize that already is a completed square. That is the square of x plus 1, or sorry, u plus 1. That can be factored. So I can write this as du over u plus 1 squared, like that. But now, if u plus 1 is being squared, I can also write that as the integral of u plus 1 to the minus 2 du. And that's something I know how to do. Now, in this case, you can just use the power rule. Some people are going to want to substitute here again, and that is fine. Be mindful of the fact that we've already substituted once, so u is already being used. So if you want to substitute again, use a different letter. W is a common choice. It's almost like a pun, right? The first one is U. What about the second one? Well, that's double U, right? You can choose any letter you like. Here, it's okay if you just want to use the power rule and say, okay, well, let me add 1 to the power, divide by the new power. But since that is something other than just a single variable, some people might actually want to write it as a substitution. That's basically the difference between, do I want to do this step in my head or do I want to write it out? If you do it in your head, great, but I'm the professor and I can't skip steps. So let me go ahead and show the substitution here. I'm going to take this u plus 1 and I'm going to call it something else. And like I said, I'm going to choose the letter w. It's equal to u plus 1. So dw is going to equal to du. All right, the derivative of u plus 1 is just 1 times du. So I could write 1 du, but I can just write du instead. So now this is going to become the integral of u plus 1, well, that's just w, to the minus 2, and then that du is interchangeable with that dw. Okay, so now how to do that. This one, using the power rule, I can add 1 to the power. So that's going to be w to the minus 1 over, divide by the new power, which I can always write as negative 1 over w. Okay, but now I can back substitute. Because, of course, that means that I get negative 1 over, w is a stand-in for u plus 1. So let me write that as u plus 1. Oh yeah, but remember, the original substitution had this u standing for e to the x. Okay, so now let me back substitute again, and that's going to give me minus 1 over e to the x plus 1. Plus my constant of integration. Okay, just like that. Note, if you had done this step in your head, you would have skipped this entire part here, and you would have just said, oh, okay, if I'm going to integrate this part using the power rule, I would add 1 to the power and then divide by the new power. So that would give me u plus 1 to the minus 1 over minus 1. That minus 1 means it's part of the denominator, so I write it as minus 1 over u plus 1. Okay? So if you had skipped that step, you would jump directly from here to here, and then you would say, okay, well now u is e to the x, so pop that back in. If you don't skip that step, you use this extra bit of substitution here in blue. So either way, we get our result. And that makes us happy. So that is it for the section. Again, this is a review of techniques that we learned throughout Cal 1, and we've peppered in just a couple of things that we saw here in Cal 2, namely the arc functions, in this case the arctangent, but the arcsine and the arccosine would fit that category as well. If anybody has any questions, comments, or problems, please make a note of those and let me know during office hours or during our next meeting. And if anybody has any problems, please reach out. I hope everyone has a nice day.